All right. There's supposed to be a YouTube video here, so if you but somehow it doesn't open on this computer, so I'll just open it in on YouTube. And so this was a disaster in 1940, I think, where so the bridge collapsed. So and then one of the possible explanation of this phenomenon is that the natural frequency of the bridge coincided with the frequency of the wind, and it led to a resonance, and because of that, the amplitude of the oscillations increased too much, and then the bridge eventually collapsed. Anyway, you can watch the video. It's very impressive. So eventually the bridge collapses. So what we are going to do today, we are going to see how to model oscillations with a second order differential equation, and we are going to try to analyze this type of cases. So a resonance, so when doesn't happen, and what is the model behind the resonance. Okay, so before we do that, let's begin with some simple stuff. Right? So let's review some basic physics. Newton's first law of motion. And so if an object is moving at a constant speed, then the forces acting on it are balanced, right? So by balanced forces, I mean that all forces are vectors. So forces are probably like arrows. All right, and then these forces, the sum of the sum of all the forces as vectors acting on an object is 0. So this is the first law of motion, right? So the second law of motion that we are going to need to is that the force equals acceleration times mass. Well, strictly speaking, acceleration comes first here. So acceleration equals force times the mass. So the force is somehow is given, and then we can figure out acceleration. But anyway, so that's one example of that law. So that the weight is the acceleration due to gravity times mass. So, and another example of this is Hooke's law. So in Hooke's law, the force acting on an object attached to a spring, right? So it is proportional to the displacement of the string. Now, some notations here that in questions related to real life or to physics, it is important to keep track of notations and of units of measurement. So here time is measured in seconds, for example. Well, it may be measured in minutes. So if, say, time is measured in minutes and distance is measured in, I don't know, kilometers instead, so then speed is going to be measured in kilometers per minute. But you need to be consistent. So if you fix the units for time, and you fix the unit for distance, and you fix the units for mass, then the units for speed and the units for acceleration and the units for force and spring constant and so on, they will be derived from this. Then you have a textbook, and the textbook is American, so it kind of uses different system of measurement. Well, some things about this imperial system, they are, well, more or less clear. I mean, the time is measured in the same units, in seconds. Distance is measured in feet. So if and a foot is, well, whatever, is 30 something centimeters. Well, then the speed is, of course, measured in feet per second, and so on and so forth. But the important thing is that, and it is kind of counterintuitive, and I didn't know about it until I had to teach this course for the first time, and then I noticed that some answers in the textbook, they looked weird to me, and then I tried to dig it, and then I realized that, as a matter of fact, pounds are not units of mass, but pounds are units of force in imperial system. So, but then it means that the mass in imperial system is measured in strange units, is pounds times seconds squared over feet. So it is kind of strange. So please, when you solve questions from the textbook, be aware that the force is measured in pounds rather than mass is measured in pounds, right? So mass is measured in kilograms, force is measured in pounds.